Good day, viewers at home. Today we are going to be calculating the energy released during nuclear fission reaction. For example, a fission reaction equation is as stated below. We have uranium-235 bombarded with neutron, and the products are rubidium-93, cesium-141, and 2 neutrons plus energy. Then use the following information to calculate the energy release in the reaction. On the table here, we have the particles involved in the nuclear fission reaction, which are uranium-235, cesium-141, rubidium-93, and neutrons. And the mass of this particle multiplied by 10 raised to the power minus 27 kilograms are 390.173 for uranium-235, 233.9274 for cesium-141, and 154.248 for rubidium, 1.675 for neutron. We are also given the speed of light, which is represented by c, to be equal to 3.0 times 10 raised to the power 8 meters per second. Solution. The first thing we are going to do is to calculate the total mass of the reactants. And the reactants in this equation are uranium-235 and neutron. And the mass of uranium-235 is given as 390.173. If we add it with the mass of neutron, which is 1.675, multiplied by 10 raised to the power minus 27. When you add up the mass of the uranium-235 and the neutron, we are going to have 391.848 times 10 raised to the power minus 27 kilogram. This is the mass of the reactants. Now the next thing we are going to do, we are going to calculate the total mass of products. And here the products are rubidium-93, cesium-141, and 2 neutrons. So we are going to calculate for that. Now the mass of rubidium is 154.248 plus the mass of cesium-141 is 233.927 plus the mass of 2 neutrons. Since it's 2 neutrons, we are going to have 2 times 1.675, and everything is times 10 raised to the power minus 27. Now, if we add up the mass of rubidium and cesium, we are going to have 388.175 plus 2 multiplied by 1.675, that will give us 3.35 times 10 raised to the power minus 27 kilograms. So if you add up this and this, we are going to have the total mass of the product to be 391.525 times 10 raised to the power minus 27 kilogram. This is the mass of the product. Now, the next thing we are going to do is to calculate for the mass defect. That is the difference between the mass of the product and the mass of the reactant. Here you will see that the mass of the reactant is slightly greater than the mass of the product. So to get the mass defect, we are going to use the mass of the reactant and the mass of the product. We subtract the two of them. So mass of reactant is 391.848 times 10 raised to the power minus 27 minus the mass of the product, which is 391.525 times 10 raised to the power minus 27. Then if you subtract correctly, you are going to have the mass defect to be 0.323 times 10 raised to the power minus 27 kilogram. This is the mass defect. So from the mass defect, we can calculate the energy release during the nuclear fission reaction. So the energy release is equal to change in mc squared. This is Einstein mass energy equation, and that involved the mass defect, which is 0.323 times 10 raised to the power minus 27 multiplied by the speed of light square. And the speed of light is 3 times 10 raised to the power 8 square. And this will give us 0.323 times 10 raised to the power minus 27 times, if we square 3, you are going to have 9 times 10 raised to the power 16. And if you multiply 0.323 by 9, we are going to have 2.907 multiplied by minus 27 plus 16, that gives us minus 11 joules. So this is the energy release during the nuclear fission reaction. Thank you.